Okay, in order to for us to keep on schedule today, we're going to go ahead and get started here. For those of you, I want to thank everybody for coming, because what you're going to see today is a culmination of basically a whole year of work from both of these teams that we have going on here. They designed the airplane last semester in the 420 class. This semester, then they validated their design by building a wind tunnel model and put it in the wind tunnel, tested it, then made modifications based on that data so that they could see if there was something else that they could improve the performance of their airplane. And they tested it again, and now they're going to make recommendations as to what the first flight test articles should look like. Another thing that's really neat about this session and the session that happens at the end of the fall semester is that the grades that are given to them, about at least 20% of their grade, is not given to them by faculty. They're given to them by the panel that we have here from industry, which is really, really neat for them to be able to present their data to people that know exactly what they're talking about. So, speaking of the panel, I'm going to let them introduce themselves since we have a lot of members today on the panel, which is great, and a very, very diverse panel. I'll let them introduce, tell you who they are and where they're from and maybe their job titles, and then we'll get started.
Good morning. I'm Travis Saloa. I'm the Director of Aviation Procedures and UAS Training at In-Situ, subsidiary of Boeing.
Good morning. I'm Tristan Corris. I'm an engineer at Lockheed Martin Skunk Works. Daniel Caraway, Lockheed Martin Skunk Works, Flight Controls.
Good morning, Chris Liebman, F-22 Flight Sciences Lead Engineer.
Bryce Mills, I'm a structures engineer at Edwards.
Good morning, Bill Zwick from Embry-Riddle, Aerospace Engineering.
Morning, I'm Scott Wells from Raytheon Missile Systems in Tucson. I'm a lead autopilot engineer.
Morning, I'm AJ Olson. I'm a project engineer with Sierra Nevada Corporation up in Denver.
Morning, Kenny Young from Boeing Mesa. I'm a manager now, but before that, I was an aerospace engineer licensed engineer.
Kenny used to be a structures guy, so I don't know. Okay, just again to let you know what you're seeing today, when they first started this a year ago, they basically were given just a set of performance parameters. The airplane has to do this, 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 and this. And that's all they were given to design the entire aircraft. So they're going to talk about that today. The first airplane that we have, I gave them, they had to take off from a carrier. It had to be refuelable to both Navy and Air Force airplanes, and it had to be tactical. It had to have a lot of range, and they will tell you all about that. So the first group that we have is our Joint Tactical Air Tanker, or JTAT.
Thank you, Dr. Ashworth. Good morning, everybody. We are Nemain Aviation, and today we'll be presenting the wind tunnel results for the Joint Tactical Air Tanker, or the JTAT. Throughout the presentation, on your left is the primary screen, and the right is the secondary. So for our roles and members, my name is Spencer Carroll. I'm the design team lead. We have Bailey Sims, Noah Garcia Brown, Joe Whipple, Emma Schneider, Dominic Lammers, Jacob Crittenden, and Marcus Ross. Here's a brief overview of what we're presenting today on the primary screen. We're going over our aircraft configuration, which was based on our parameters from the preliminary design, the predicted preliminary design performance, our initial wind tunnel model, which again is based on that preliminary design, our test 1 and test 2 procedures, which will account for both tests, test 1 wind tunnel results, which is referred to as T1 throughout this presentation, the test 2 wind tunnel results, which is referred to as T2 throughout this presentation. So for our motivation and mission, the Department of Defense needs a tanker that is both joint capable, which means it will be able to refuel Air Force and Navy jets. It is also needs to be tactical, so it can fly closer to the combat zones than the current tankers can. It needs to be carrier capable, which means it needs to launch, land, and be stored under deck of the carrier. So for our mission requirements, we do have to take off and land on a short dirt runway or an aircraft carrier. We need a 600 nautical mile radius. We need to be able to be refueled by another heavy tanker. We have to refuel at Mach 0.5 to 0.8, and we have to deliver at least 40,000 pounds of fuel. We also must be stored at within a two-fighter space under the deck of an aircraft carrier. On the secondary screen is a typical mission profile for the JTAT. So for our aircraft configuration from our preliminary design phase, we chose a high wing with a mid-T tail, as you can see on the primary screen, and then all dimensions are in inches. To fit within this two-fighter space, we had to be within 60 feet length, and then 60 feet again in width, so we have a fold within our wing to meet that requirement because our wing span is at 82 feet. On the secondary screen are some plane specifications that are not on the primary. So again, we have to use the flying boom system and probe-and-drogue to refuel both the Air Force and Navy jets that are both stored within the tail of our aircraft, as you can see on the primary and secondary screens. Next up with our predicted preliminary design performance is Jake.
Thank you, Spencer. Throughout the next couple of series of slides, this data that is shown is going to be for our preliminary design that we were using to prove our concept of design. On the primary screen, you'll see our thrust available, thrust required plots at sea level. These were to show that we would have the excess power to be able to achieve our requirements of being able to refuel at Mach 0.8. Mach 0.8 is denoted below on both of the slides. The same goes for these slides at 30, on the secondary slide, on the left for our thrust available thrust required at 30,000 feet. For our specific excess power contours, we predicted that we'd be able to have a maximum ceiling of 55,000 feet, meeting our requirement of being able to refuel up to 30,000 feet. On the secondary side is our flight envelope, which would be our key maneuvering points per our design. For our takeoff and landing, being able to take off and land on a short runway, dirt, or asphalt, we do meet our requirements of being under 5,000 feet. For our range prediction, the key point here is that we would design our aircraft to be able to deliver up to 24,000 pounds of fuel at 600 nautical miles, and still have enough excess fuel to fly and land or loiter around an ultimate. For our static stability requirements, on the primary side is our CM versus alpha plot. In this plot, we were required to be negative, therefore we would be stable, and we predicted that we'd be able to meet this requirement. Also, the same goes for our CL versus beta plots, being able to have a stability here in a negative slope. We do meet this requirement. On the secondary side is our CM versus beta plots, which would be positive and have a positive slope, having a positive trend, showing that we would also be stable here. Next, I'll hand it on to Marcus Ross for initial wind tunnel result model.
Thank you, Jacob. Shown on the primary screen is a ghost view of our initial wind tunnel model with the structure shown, as well as several dimensions for the wind tunnel model. This wind tunnel model was based off of the preliminary design. A scale of 1 to 34 was chosen based off of considerations such as wind tunnel blockage, weight, and the load limits of the force balance, and to provide adequate structure for the wind tunnel model. Shown on the secondary screen is a photo of our initial wind tunnel model. This wind tunnel model was printed, or had pieces printed in ABS plastic on 3D printers, as well as a steel wind tunnel structure. The wind tunnel model is broken up into 3 sub-assemblies, the first of which is the wing assembly. Shown on the primary screen is an exploded view of this wing assembly. It consists of 6 3D printed parts, as well as a steel wind tunnel structure that helps the wing in bending during wind tunnel testing. I now show a video of how it is assembled. First, we assemble 1/2 the wing. Next, we insert the internal structure into this wing half. Then we attach the second half of the wing, and finally we attach the nacelles. Shown on the secondary screen are the 3 sub-assemblies of the wind tunnel model: the tail assembly, the wing assembly, and the fuselage assembly. Shown on the primary screen is the tail assembly. It consists of 3 3D printed parts, a vertical tail and 2 horizontal tail pieces. The internal structure consists of a vertical tail plate that reinforces the vertical tail and 2 small steel rods that reinforce the horizontal tail. And now show a video of how it is assembled. First, the steel rods are inserted into one of the horizontal tail pieces, and the vertical tail plate is inserted into the vertical tail. Finally, both horizontal tail pieces are attached to the vertical tail. Shown on the primary screen is the fuselage assembly. It consists of 3 3D printed parts, as well as the steel internal structure. This steel internal structure is what allows the wind tunnel model to mount to the force balance, and the steel internal structure reinforces these 3D printed pieces. I'll show you a video of how this one is assembled as well. First, the tail and some of the internal structure is attached to the center fuselage, and then the rest of the internal structure is attached to the fuselage using screws and epoxy. Finally, the nose is attached to the fuselage using some steel rods. Once all these assemblies are created, the wing and the tail must be mounted to the fuselage. This is done using some screws. Here's a video showing how it is assembled. It's pretty straightforward. Shown on the secondary screen are 2 3D printed caps for when we are testing without the tail or without the wing. These caps fill the gaps left by these sub-assemblies. They are attached using the same screws as the wing and the tail. After the model was assembled, the surface of the model was sanded smooth and then painted with several coats of primer. Finally, we painted a black finish coat on the wind tunnel model. This allows us to have a contrast between the tufts applied to the aircraft later and the wind tunnel model. These tufts that were applied to the model are used to aid us in flow visualization. They are spaced 1 inch apart and are 1 inch long. And I'll pass it on to Emma for wind tunnel test procedures.
Thank you, Marcus. The procedure I'm going over was used for both our first and second tests. In order to be able to test our model in the wind tunnel, we needed to determine what velocity to run the wind tunnel at. We did 2 different tests for this, the first of which was a structural integrity test of our model. We inverted it and we simulated wing loading using 1-pound sandbags in a distributed load. We ended up being able to, until the wing tips deflected 1 inch, we were able to put 56 pounds onto our wing before it deflected. The maximum weight for our pyramidal balance is actually 40 pounds, and so we used that 40 pound to determine a velocity of 192 feet per second for the tunnel. The second of these tests was the most restrictive. It was an aeroelasticity test. We put the model in the wind tunnel at our maximum angle of attack, which is 24 degrees. We increased the speed on the wind tunnel until there was visible flutter in the wings and the tail. And this happened right after 98 feet per second, which is 30 meters per second in the tunnel. For both of our tests, we tested 3 different configurations. On the primary screen, figure A shows our full configuration, figure B shows our fuselage wing configuration, and figure C shows our fuselage only configuration. All 3 configurations were tested at a full angle of attack range, which is -4 to 24 in 2 degree increments, and a full side slip range, which is 0 to -10 in 2 degree increments. On the primary screen is an example of what our testing setup would look like. We have a testing section of around 32 by 45 inches, and we collected our data using an ERAU-Lab data collection system. On the secondary screen is a picture of the pyramidal force balance we used to collect the ERAU loads within the tunnel. Denoted is the beta adjustment knob. The reason this is denoted is because we had to manually adjust it for both tests. we had two different camera placements to capture our
Gotta have supervision.
we had two different camera placements to capture our plane within the tests. Both of the photos behind me are taken with the wing fuselage configuration at -10 beta. The primary screen shows our side view, which was meant to capture the flow on the nacelles and on this fuselage. Our top view was supposed to capture the flow on the wings. This helped us see stall as well as other separation off the model. Up next will be Noah Brown with our wind tunnel results.
Thank you, Emma. The following section, I will be comparing the data acquired during our initial wind tunnel test to the performance data that was calculated during our preliminary design phase. All the data that I am about to show you now has undergone Reynolds number corrections. On the primary screen is a picture of our wind tunnel model in the preliminary design configuration. On the primary screen is a rendering of our aircraft in the preliminary design configuration, and on the secondary screen is our wind tunnel model. On the primary screen is a comparison of our lift curve. The lift from the tests was quite different from what was initially predicted in the preliminary design phase. The only similarity was the lift curve slope. The stall angle has increased from about 13 degrees to about 18 degrees. On the secondary screen is a flow visualization of our stall at 18 degrees angle of attack. Next up is our coefficient of drag on the primary screen. Most of this drag we predict came from the unmatched Reynolds number as well as the flow-through engine nacelles. On the secondary screen is a picture of a flow visualization of our engine nacelles. This was an issue we will address after the test. On the primary screen is our CM versus alpha plot for the initial wind tunnel test, comparing it to our preliminary data. As shown, the CM alpha slope from the test data is a lot less than what was initially predicted. This could likely be due to the size of our horizontal tail. On the secondary screen is a flow visualization at 12 degrees angle of attack. Next up is our CM versus beta plot for the initial test. As shown, the slope is negative, which indicates that the JTAT is unstable in yaw, which is contrary to what was initially predicted in the preliminary design phase. This is most likely due to the small size of the vertical tail as well as the mid-mounting of the horizontal tail. On the secondary screen is our CL versus beta plot. It can also be seen that our slope is much more neutral than what we had initially predicted. Next up on the primary screen compares our thrust available, thrust required at sea level. It can be seen that we have considerably more drag as expected compared to what we had initially predicted. The thrust available, thrust required using our predicted data intersects at a velocity lower than 530 knots, which is below Mach 0.8. So using the wind tunnel data, the JTAT would not be able to meet its required speed at sea level. However, on the secondary screen, which is thrust available, thrust required taken at 30,000 feet, we do still have excess thrust at 470 knots, which is Mach 0.8 at 30,000 feet. So even with the wind tunnel data, the JTAT is still able to reach its required speed at 30,000 feet. On the primary screen is our predicted flight envelope, and on the secondary screen is our test 1 flight envelope. Due to the decreased lift, the stall limits have gotten a lower slope in the test data compared to the predicted data. The Q limits have also been decreased due to the slight increase in drag. Next up on the primary screen is our specific excess power that was initially predicted. On the secondary screen is our specific excess power using our initial wind tunnel test data. Due to the reduction in drag, due to the increase in drag, the predicted absolute ceiling has been decreased slightly. On the primary screen is a breakdown of our fuel usage, both using our predicted data from the preliminary design phase as well as the test 1 data. As shown, the predicted fuel offload has been decreased in order to maintain the 600 nautical mile combat radius that was initially required. On the secondary screen is a visualization of our fuel usage throughout the mission. On the primary screen is a comparison of our takeoff verification, both using the predicted data and our test 1 data on both our concrete and dirt surfaces. It can be seen that we still meet our requirement using both sets of data. On the secondary screen is our landing prediction comparison using both our preliminary predicted test data and our test data. And in this case too, we also meet our required runway distance. I will now go over the recommended changes we made following our initial wind tunnel test data. On the primary screen goes over our redesigned empennage. This was done to address our negative CN beta slope. We increased the root chord length of our vertical tail, which increased the overall effective area. This also changed our aspect ratio and our taper ratio. We also added end caps to the horizontal tail to increase our overall effective vertical tail area. And we also adjusted the horizontal tail to match the increase in size of the vertical tail. On the secondary screen, we have our nacelle redesign. The pylons were redesigned to be more streamlined, so they have less blunt body characteristics. The nacelle itself was also given an airfoil shape in order to reduce the flow separation. Here is a 3-view of our aircraft with the modifications made to it. You can take the you can see the modified tail section as well as the modified engine pylons and engine nacelles. I will now pass it on to Dominic Lammers to go over our second wind tunnel test result.
Thank you, Noah. Over the course of these next few slides, I'll be comparing our initial wind tunnel test, test 1, on the secondary screen, and on the primary screen will be our test 2 data. Rendering our pictures of both of these models are shown on the respective slides. On the primary screen is our lift curve slope for test 1 and test 2 for comparison. The lift curve did not change noticeably in the angle of attack where it stalled or in the CL max. On the secondary screen, you can see there is a slight change in our lift curve due to the engines. The difference between the red dotted line and the blue solid line is our redesigned nacelles. Those are the only difference between these two lines, and as you can see in the leading up to the stall, there's a slight increase in the lift curve characteristics. On On the primary screen is our coefficient of pitch versus alpha. The green and the blue, green and the yellow lines denote the full configuration. And as you can see from test 1 to test 2, there's a slight increase in our coefficient of pitching characteristics. The CM naught value decreased, and the slope of the CM versus alpha plot increased slightly. On the secondary screen is comparison of our JTAT from test 1 to test 2. The nacelles are noted at an angle of attack of 4 degrees in test 1, where the flow detached became turbulent on the nacelles. In test 2, the flow remained attached to the nacelles up to an angle of attack of 12 degrees. This gave us an increase in our lift and pitching moment I previously noted. On the primary screen is our coefficient of drag versus alpha. Noted at 4 degrees angle of attack, there was a 25% decrease between test 1 and test 2. On the secondary screen shows where this drag reduction came from. The test 2 data and the wing and fuselage only for test 1 and test 2 lie on pretty much the same line. This means that the addition of the empennage did not cause an increase in drag in this test, whereas before in test 1, there was an increase in drag when the empennage was attached to the JTAT. On the primary screen is our coefficient of roll versus beta, comparison between test 1 and test 2. For the wing and fuselage only configurations, the JTAT did change from being unstable to stable, and in the full configuration, we are stable in roll. This is noted in the green line. On the primary screen is our coefficient of yaw versus beta. The green line denotes our full configuration for test 2, which we are stable now since it is a positive slope, and the yellow line was our previous test 1 result, which was negative, where we were unstable in yaw. On the primary screen is the thrust available, thrust required comparison between test 1 and test 2. Predicted data is also shown on there for comparison. Due to the decrease in drag, the JTAT does have more thrust of it, excess power at sea level and 30,000 feet. At 530 knots, we do have excess thrust, so we can cruise at this velocity. On the secondary screen is our thrust available, thrust required at 30,000 feet, and we are still able to meet our requirement of Mach 0.8 at 30,000 feet. On the primary screen is our test 2 flight envelope, and for comparison is our test 1 flight envelope on the secondary screen. Due to the reduction in drag, our maximum velocities did increase slightly. On the primary screen is our specific excess power contours for our second test. Due to the reduction in drag, our maximum absolute ceiling increased to 55,000 feet. And on the secondary screen, for comparison, is our test 1 specific excess power contours. On the primary screen is our fuel usage for the predicted test 1 and test 2 over the course of a normal JTAT flight. With the test 2 data, we are now able to offload 23,600 pounds of fuel at our 600 nautical mile radius. We are also able to offload 40,000 pounds of fuel directly over the carrier, which meets our RFP requirements. On the secondary screen shows the normal flight for a JTAT. On the primary screen shows our takeoff comparison from test 1 and test 2. Both tests did meet our 5,000 foot requirement. On the secondary screen is a comparison from our test 1 to test 2 landing distances, and both of these still meet our requirement of 5,000 feet or less. I will now pass it off to Joe for structural analysis.
Thanks, Jonathan. On the primary screen, you can see the structural layout of the JTAT. This is a ghost view. On the secondary screen is the fuselage structural design. There is frames spaced out every 24 inches with stringers along the length of the fuselage every 10 inches. On the primary screen is a VN diagram with gust lines overlaid. These main points in the gust lines lay inside the flight envelope, meaning they're not constrictive to our max loading. And during the structural analysis of the wing, the first step was to find the distributed load, distributed lift on the wing. To find this, we use strength approximation, which is an average of trapezoidal and elliptical lift distribution. It is assumed that the JTAT's lift is carrying 100% of the weight of the aircraft, plus or multiplied by the 3 Gs and a factor of safety of 1.5. On the primary screen is the wing shear diagram throughout the length of the wing. The shear diagram takes into account for the distributed lift along with the fuel weight, the weight of the engine, and the predicted structural weight of the wing. On the secondary screen is the moment diagram, and you can see the placement of the fuel weight and the engine by the change of slope. Using the shear and moment diagrams, the sizing of the front and rear spar was able to be calculated. The front spar is at 15%, and the rear spar is at 60%. These locations were chosen due to control surfaces, flaps, and leading edge slats. The spar caps, the areas are shown on the primary screen. The caps are designed to resist bending moment, and the webs are to resist the shear. The material used is aluminum 775, T6 aluminum. On the secondary screen, you can see the structural layout of the wing. The rib spacing is 24 inches. At the base of the wing, the ribs are straight, and that is inside the wing box. And then outside on the wing, the ribs are 90 degrees off the front spar until about 11 feet off from the wingtip. Where the wingtip needs to fold, that rib is straight. Next, Bailey will continue with the structural analysis and the ANSYS model.
Thank you, Joe. For the structural analysis of the horizontal tail, the lift distribution was calculated similarly to the wing using Schrenk's approximation. The maximum lift force on the wing was calculated by finding the angle of attack that the horizontal tail would experience during a 3G limit load maneuver and using this angle of attack to calculate the maximum lift force on the wing. On the secondary screen is a structural view of our entire empennage. This includes the structures for our horizontal tail, our vertical tail, and the vertical end caps on the edge of the horizontal tail. On the primary screen now is our horizontal tail's shear diagram. Of note on this diagram is that before the end of the wingtip, the shear does become positive. This is due to the fact that the shear due to the weight of the end caps on the horizontal tail exceeds the lift force on the wing at this point. On the secondary screen is our horizontal tail's moment diagram. On the primary screen now is our horizontal tail spar dimensions. The cap areas shown are for the root of the spars, are at the root of the wing for the spars. And again, this is using 7075 aluminum. On the secondary screen is the structural layout for the horizontal tail. Space has been cut out of the structure to allow for the elevators. And again, the rib spacing is 24 inches for the horizontal tail. On the primary screen now is our ANSYS model for the structural layout of the wing. ANSYS was used to verify all hand calculations and to verify the overall structural integrity of our wing. Using a convergence study, we were able to conclude that the solver had converged on a solution. Again, of note is that at 11 feet from the wingtip, there is a straight spar. The max stress on the wing, shown on the primary screen, was found at the root, and this was 72,000 psi, and this is below the yield strength of aluminum 7075. On the secondary screen is the total displacement for the ANSYS wing. The The maximum deflection was found at the wingtip to be just above 40 inches. A similar analysis was done for the horizontal tail. A lift distribution was applied between each of the spars, and the max stress was found at the root of the wing to be 54,500 psi. This is again below the yield strength of aluminum 7075. On the secondary screen is the total displacement for the horizontal tail. This total displacement was found. This had a maximum total displacement at the wingtip of 7 inches. I'll now hand it back to Spencer to go over our cost analysis.
Thank you, David. So cost analysis was done to determine the cost of a JTAT. Per unit cost is about $110 million, and we produced 50 planes over a 5-year period, which comes to a total cost of $5.5 billion. On the secondary screen is a cost accumulation of the hourly accumulation and the fixed costs. So for our labor accounting for the group, on the primary screen, you can see a graph of the hours we put in this semester. The solid line is the predicted hours, and the dashed line is our actual hours. There is a slight decrease because in the beginning of the semester we started off a little slow, but since then we've kept a solid pace. On the secondary screen is a cost estimation by hour and an hour breakdown for the jobs that we've done. So for our conclusions and recommendations. We concluded that the redesign of the empennage did improve the performance of the JTAT by reducing drag and increasing our roll and yaw stability. The nacelle redesign reduced the flow separation from our flow visualizations, and it did improve the lift curve. The structural design does meet the load expectations that we expect the JTAT to see, and the JTAT does meet all of its mission requirements with these changes. So our recommended flight test article will have the redesigned nacelle and pylon, as well as the redesigned nacelle, or empennage, since they did improve our performance such that we can meet our requirements. Any possible further investigation we would like to see would be into the horizontal tail end plates, the pylons, and the nacelles. We would like to see those optimized and see what kind of options we can get to further improve the performance of our plane. And then we would like to wind tunnel test in transonic regions, since we will have to perform in those transonic regions and confirm our results. Are there any questions?
Okay, good job, guys. Since we have, let's see, 5, 6, 7, 8 panel members out here today to ask questions, if you would please look at your most burning questions, ask those, pass it on, and then if you have others and we have time for those, then we'll come back to you.
I'm going to defer first.
Good job, everyone. Great presentation. Just a few things. Let's start with slide 28B, please. Can we go back to that? The wind tunnel model here. How did you properly take out your tear data for the adapter mount that you created there? Since it looked like on the screen over here, it looked like from the build that you couldn't. That once you added that to the model, it wasn't able to come off to actually take the tear data out of that.
So for our tear data, we didn't actually take any tear data from that stand in between the model and the force balance. It was considered small, and we did take that into account when we were doing our data analysis, that is also a cause of changing the forces and drag. We did take tear data of, what you don't see in this picture, is that between the model and the floor of the tunnel, there is a significant extrusion for the force balance itself, and so we did take tear data for that.
Okay. Is there a reason you created that adapter mount to begin with? From the size of the fuselage, you probably could have just directly adapted that to the sting balance so that you could especially when you're converting your data for corrections for your CG and all that. It would probably have reduced a lot of the errors. Just a comment. One more, and then I'll move on. Slide 52B. I know it's just a rendering, but be careful with some renderings because, especially in the back there with the hook system you have there, one, I've never seen one with an opening back there, and most people will probably tell you that that will fail on landing. So I understand as an AVGen you didn't do any analysis to actually design a hook system, but just be careful with renderings because it might give you the wrong idea of, or the panel the wrong idea of, because an experienced Navy person will look at that and be like, I'm not going to fly that plane with that hook system because I will not be able to land. Just a comment. But otherwise, good job, guys.
I'll reiterate, good presentation, like all the work that you guys did. Two slides we'll look at real quick. Slide 36, and this goes to kind of your static stability coefficients. So your predicted values, if we look kind of order of magnitude, and then we go to slide 49. If you flip back and forth, you'll see it's about an order of magnitude difference. So did you guys look into that at all? Why they were so different?
We did test at a lot lower running number than we will be flying at, so that could have been it. But other than that, we do not look into it.
Okay, so just a recommendation, kind of take the extra step there next time to compare those, because what I actually noticed in all the coefficients, they're actually almost all an order of magnitude off, so it tells me there may be a slight error in the calculation, reference lengths, some of that stuff. So just kind of double check those numbers, because those are red flags that we see in presentations sometimes. Lastly, I really liked what you guys did with the performance analysis update, right? So you took your wind tunnel data, you went back, you looked at the performance, you looked at the impacts to it. That's kind of the extra step that we look for of answering the why. How does your data kind of correlate based on what was predicted? So great job with that.
Awesome. I will continue to echo that. You guys put in a huge amount of work. I really appreciate the efforts that you made to improve the deficiencies that wind tunnel testing revealed. I want to talk a little bit about CN beta. In fact, that's all my questions. So let's, right, one question. Slide 37, you said that the tail was too small. Now, I'm looking at your data and I'm trying to substantiate your conclusion with the data that we've got there. Because what I see is that the real detractor from CN beta was actually the wing and fuselage. And I'm like, all right, well, there must be something about the wing and fuselage that's substantially destabilizing. So I'm curious what you guys think. What on the wing and fuselage is really destabilizing?
We believe that it was the nacelles because they caused so much separation.
Bingo. Yes, completely agree. So be a little bit careful about saying that our tail was too small. No, it's sort of it. It's more that the nacelles were too big. However, you're kind of rocking a hard place, right? Because I don't think that you can necessarily shrink the nacelles. And I don't know if your CG is going to allow you to move the nacelles back. So the only way to overcome too large nacelles is to increase the size of your tail. So your solution of increasing the size of the tail was right, but the reason you did it, I think maybe you could have articulated that a little better. And so then we go to slide 52. And I wanted to ask, the green line there has discontinuities at 4, 6, and 8 degrees of beta. If I remember right, you were doing your increments at every 2 degrees, but something happened at 4 degrees of beta. Do you have any idea, any speculation about what it is that's causing that?
This yaw moment could have been due to the thrust drag, due to the flow through nacelles. It would cause a yaw moment until the vertical tail hadn't created enough yaw moment to overtake that.
Gotcha. Okay. Cool. One thing to think about, the aircraft is unstable until you get to about 4 degrees of beta. So that means the nose is going to start creeping out before it comes back, which is really scary if you think about it from the cockpit. So you may need to take additional measures to get a stable CN beta line the whole time. Final, this is a very short comment in response to you. The data that you showed, I wish that you would show data points. When you're gathering empirical data from an actual test, please show points rather than curves, because the curve makes it look like it might be an equation, whereas the points are more obvious. Thank you, guys.
I want to echo the great job. It's a lot of work into this. I just have a quick question. So, we go to slide 63A, please. So, the yield strength for the metal you use is 73 KSI. Can you go to slide 68A? So, you have 72 KSI max stress. Your yield strength is 73. What was the load condition for this? Was this just, did you say it was just the 1G lift distribution, or was this for your max G that you're rated to?
So this was for 3Gs and effective safety of 1.5.
Okay, gotcha. I missed that part. Okay, a little less concerning now. All right, that was it. I think you guys did a great job.
That was my question as well. Still, only 1,000 PSI difference there between yield and max stresses. It gives me the shimmies right now.
Good job. I assume you're carrying a gajillion pounds of fuel to offload, but I don't see anywhere how much weight that is. And how does your CG change as you start unloading fuel? And how does CM alpha change during that fuel unloading?
So we actually did that analysis in our preliminary design. We do have those slides available if you'd like to see those in both our other presentations.
All right, that's fine. So I think I had just this is a slight chart nit. When you show stuff like your CM alpha plot, what configuration was that? Where was the CG? What was your flight condition? Because here's what's going to happen in industry. You're going to create that plot. 4 years from now, you're going to be sitting in a meeting and somebody's going to use that plot to show what CM alpha is at a condition that was completely different than what you meant it for. And if you include something on there that says, this is my condition, then when somebody goes out and lifts that chart and uses it for something else, you won't get confused by the data.
Nice job, guys. You made comments on slide 25B that Tufts tripped the boundary layer. Is that the right way to accomplish boundary layer control on the wind tunnel model? And is that the right thing to use for a force moment capture?
So we were attempting to emulate the Reynolds number effects of our full-scale aircraft, which would have had a turbulent boundary layer, and this is why we attempted to use the top to strip the boundary layer.
Okay, that's right in general, but be careful because Tufts are meant for full visualization. They're not meant for boundary layer control and force moment captures. So your low-speed wind tunnel book or Farway and book does a really good job of talking about grid strips, trip heights, things like that, where the sheet puts in the wing. That's a more typical, traditional, appropriate manner for force moment calculation. Great job.
I'll echo the congratulations on all the hard work and effort put in. Pretty simple question. Slide 68. You guys were showing your analytical model for bending moment at your wing root, yet you guys have a folding wing tip. So what is the moment going into your folding wing tip fitting? For our ANSYS analysis, we assumed a solid for the entire wing with perfect joints at every point. So this does not account for any mechanisms that would occur at the wing fold or any separations in the structure at the wing fold.
Okay. I kind of figured as much given your time constraints, but something to be mindful of, especially if you have a folding wing consideration. You're not going to have a perfectly straight spar lofted up there like you have. Okay. But great job, guys.
All right, I'll do a little bit of admin cleanup before I do that. Did you guys consider what's the outboard length of your wing at the fold point? How much wing is out there?
It's 11 feet.
On each side.
On each side.
From the tip.
Okay. So what's the height of the maintenance deck on a carrier that you're going to be storing your airplane?
So it's 18.5 feet. So at the fold, it actually folds underneath to where that maximum height is.
Right. Is there an ability to unfold
Yes.
in that maintenance deck? Is there enough space?
In our CATIA model, and in one of the vendors it's shown, we can have it fold in CATIA. While I was doing that and creating that model, I did have the wings folded at 90 degrees up, which would be the extreme height that they would reach, and that is below the maximum underdeck height.
Okay.
So it would be able to fold and unfold under the deck of the aircraft carrier.
Good. I'm glad you guys at least thought through that a little bit, because the last thing you want to do is hamstring the maintainer trying to keep that airplane up and flyable. Be able to do all the maintenance that need to do, or cycles and so forth. So just clean up. I think your plots and your charts and everything overall, other than the specific feedback, look extremely professional. I like having the names on the slides like you guys do. That's actually something that I recommend to other groups after PDR. And then also a real nice touch, other than Dr. Ashworth being intentional. The other nice
I didn't have
touch.
a shovel to lean on. No.
The other nice touch was that those rendered videos of your wind tunnel model assembly, that was pretty cool. So I would definitely recommend that. And it shows us how you actually can configure, reconfigure your model, and you never would have thought of doing those things back when I was in school, because that would be too much time. Nice work overall. Good job.
We still got about 5 minutes if anybody. Why did I know it was going to be Chris?
All right, cool. Can you tell me, how do you know that the aero model that you had for the wind tunnel, how do you know that that was a valid model? And what I'm asking is, did you do any measurement about the curve or the dimensions or the angles, or did you do anything to compare the 3D print that you got versus the thing that you had put into CATIA? Because sometimes those 3D printers, they do their best, but.
So we didn't do any type of measurements for the curve of the wing. We did, when you run the ERAU lab software, there's inputs for CG of the model as well as CG of your theoretical models are from CATIA, and you normalize them to the pivot point on the thermal balance. And so we did do some normalizing of the CGs. We didn't do any measuring is this listed?
Is this a correct airfoil from 3D?
Sure. Yeah, so it's a completely overused phrase, but all models are wrong, some models are useful. Make sure that your model, in the places where you can check it, make sure that you do. Because there's going to be a million other sources of error that you can't check. So whatever you can do, try to do those things. That's going on. Thanks.
Sure.
All right, slide 68. So I didn't mention this to you guys before, but I actually worked in structures for about 4 or 5 years too. So coming to stress and FEMS, a couple questions I had is, what stress is this? Is this a max principle? Is it a von Mises?
As shown on the screen is von Mises stress.
Okay.
So be very careful with which one you use when you compare it to yield strengths and to ultimate strengths. This typically we'll use on VCs, I believe, for yield and max principle for ultimates. And those stresses are calculated different. Also with fins, be very careful pulling stress values. So the question I have about that is, do you know what elements you are using here? Are they 1D elements, 2D elements, 3D elements? And if so, are they first or second order?
These are 3D elements, and I'm not sure about first or second order.
Okay, so 3D elements, yes, that's what we typically do for stress. Normally not an entire wing, but you can. So something I recommend here, especially pulling stress out of a model, is go in and do a free body diagram out of the model, pull out the loads, and do a sectional analysis, right? I think on one of these plots, it showed the I-beam essentially up in the right corner. So if you actually do a sectional analysis, right, with all your bending moments, all your shear loads, you can actually compute where that stress should be and do kind of a very quick hand check of, hey, is this fin giving me what I need? As well as then we can go down the rabbit hole of mesh convergence, you know, those types of things, or boundary conditions and issues there. So, but overall, really good job doing the fin, right? And then some of the extra steps that we kind of have to do in the industry are following some of the comments and questions that I have.
First, these were designed using hand calculations and ANSYS.
Okay.
Okay, thank you very much. I've already asked all my questions. You guys know what those are, so I appreciate the audience, everybody being here, and we're going to take a short break now, and we'll start up again at 9:10 with the